Here you go.
Okay.
Welcome everyone to the Working Group 3 seminar. Today it's my pleasure to introduce José de Ramón, who is, as of very recently, at the University of Alcalá de Henares, formerly at the University of Burgos, and today he will tell us about relativistic causality in particle detector models. Please go ahead.
Well, first, thank you very much for inviting me. I tried to set up the talk in such a way that it is a nice bridge between the kind of things that the people in Working Group 3 care about and, well, all the work that has been done in the context of particle detector models. Second. There you go. Started with that. My apologies. So, well, first, what I'm going to talk about is, in general, what the detector models are and the kind of things that one calculates once a detector model is specified. I'm going to share what I understand, what I've worked on in the context of causality and signaling in particle detector models and the relation that these particle detector models have with the concept of Sorkin's impossible measurements. Then I'm going to present a rather coarse classification of what kind of detector models have a nice causal behavior. And last of all, I'm going to present some models we're working on that we think that have some nice properties in relation to causality and signaling. Second. There you go. Well, okay, detector models. So as for right now, what we know is that quantum fields as local quantum systems are let's say, have some locality structure that is defined over spacetime, cannot be thought of operationally in the same way we think about non-relativistic quantum systems. So a useful conceptual framework to talk about measurements and operations in a local way can be envisioned as probes that interact locally with the quantum field and for which we calculate the statistics after these interactions have happened. That is, we understand detector models as some kind of specification of a scattering process. What we are going to address in this talk is what is the interplay between relativistic causality and these detector models, right? So, but first, we're going to specify exactly what kind of fields we're studying here for those of you that well, this is the kind of field that has nice analytical properties that is well understood mathematically, and also that basically has as its defining feature is locality structure and its causal dynamics. That is the real scalar Klein-Gordon field defined over a globally hyperbolic spacetime. And the work that we've been doing mostly, although there's been a lot of literature, is in 3+1 dimensions. Here we have the Klein-Gordon equation and for a globally hyperbolic spacetime that can be specified by the Lambertian that is unique to that globally hyperbolic spacetime with a Lorentzian metric, a mass term, and a coupling to curvature. So in this case, we understand this field very well because the classical equations of motion, which are given by the classical equations of motion of the Klein-Gordon field with a source term, admit an advanced and a retarded solution, such that for every compactly supported function, we have a unique solution to the homogeneous problem that is supported on the future of the support of the compactly supported function, and a retarded solution, that is supported in the future, and an advanced solution that is supported in the past. So, and these operators are unique in such a way that, for instance, when we flip the arguments, what we get is that we exchange advanced and retarded solutions. In this context, a covariant way of quantizing the field is to impose the canonical commutation relations, which also imply the micro-causality action that is called. So, sorry, can you see with this thing here? Or is it just me?
Yes, we can see your pointer.
Okay. So in this case, what the one does is one imposes that the commutation relations of the field as an operator value distribution satisfy that the commutators of the fields go to a C number that is precisely given by the difference between the advanced and the retarded solutions. And you can check that when you specify the theory over a spacetime slice, that it gives you the canonical commutation relations between the field amplitude evaluated on the slice and the canonical momentum. So what is a detector model in this case? So a detector model is something that gives you an arrangement of quantum systems to which one can associate operators that depend on space and time in the interaction picture. And the fundamental object that one uses to calculate things is the so-called scattering operator, which is given by the time order exponential of this, say, we call them currents, smearing the field amplitude in space and time. So what the kind of things that, this is a very coarse summary of what the kind of things that one can do, but what one basically does is either one calculates the reduced dynamics of the detectors after the interaction, which take generally the form of a quantum channel over the detectors. And that is the trace over the field's degrees of freedom of an initially uncorrelated state of the detectors and the field. And then one implements this input that is the scattering matrix there. More recently, there is a lot of interest in knowing what kind of things a particle detector detects when, for instance, not detecting particles. And that's mathematically explained through, the calculation goes through the computation of the so-called induced observables, which give you a map between algebras of observables, not states, in which instead one traces the degrees of freedom of the detectors to know exactly what thing we're measuring when we're measuring some observable of the detector about the field. So what are the common approaches? Prominently, in this, well, at least in the context of the particle detector literature, what one does is to study the channel that the field induces over the detector's state in perturbation theory. Other approaches that are more in when one, for instance, wants to discuss things like thermalization, equilibration, and stuff like that, what one does is to describe the channel as some one parameter semigroup given by a Lindbladian operator. And this is something that it can be shown that it only holds when the time in which we're defining the dynamics is coarse-grained, because we need some notion of rotating wave approximation, Born approximation. We basically needed what is called in open quantum systems the weak coupling limit. There is lots of literature, and there's been that's given much fruit of thought about also about the so-called quantum control operations, in which the scattering matrix can become computed exactly. This is the case when the current operators associated with each detector don't actually evolve in the interaction picture, and they only depend on space and on time in a scalar way. That means that the scattering operator can be thought of as a quantum controlled unitary that acts over the field and whose form is known. And that can be, these are going to take generally the form of a phase times an exponential of the field. That is what is called in the literature a Weil operator. And there's also like many techniques that one can use with phase space analysis when the interactions are linear. Those are the so-called Gaussian operations. And as we will see later, these also admit a covariant form that I shall denote here quantum Brownian motion, or a covariant extension of the so-called quantum Brownian motion. Okay, so how am I defining causality here? So, well, I'm aware that in the literature of, well, in which the people that are in this group are more experts than me, there is a very big distinction between what one would call causality and signaling. So what I'm going to talk about here is about exclusively signaling. So I'm not going to talk about causal influences, superluminal causal influences, and that kind of thing, or what is the effect that a measurement or like a conditional measurement has on between the different statistics of different independent systems. What I'm going to talk about here is about whether local statistics of one system can infer settings of other systems without conditionalization. So in other terms, what I'm going to talk about is that the quantum informational signaling relations in the collective statistics of many detectors respect the causal structure of the background. And this makes sense only when we associate partial ordering relations to the spacetime supports of the operators of the currents that are associated with each detector. So in short, a good example would be that if we switch on a detector A strictly after another detector B in some reference frame, and that's what makes it relativistic, because we can have more than one reference frame, the local statistics of B are not affected by the settings of A. That is, if I measure something here and I don't say what it is, detector B cannot know anything about what detector A did. Note that the opposite situation is not true in general, because even if a party B doesn't communicate to the party A, the action of interacting with the system, the action of in order to measure something, even if the outcome of that measurement is not communicated, can still have some causal influence over a detector in the causal future. So this is a result that we did in our paper in 2021 with Maria Papageorgiou and Eduardo Martín Martínez. So what happens with here is that the microcausality in the field indeed enforces that a detector can only receive signals from its causal past. So therefore, microcausality enforces causal factorization of the dynamics, which has this as a consequence. We say that then very schematically, that if A is after B in some reference frame, then strictly after, then the total scattering matrix decomposes in this way, and that means that nothing that not like let's say select the non-selective operations that happen in A cannot affect B. And in particular for space-like separated detectors, because there are like two reference frames in which one goes after the other and the other after the one, that means that the total scattering matrix factorizes in this way, and also that the corresponding scattering operators commute. So there's no signaling between the detectors. So from here, we took two roads. If we're satisfied with this result, that is, that when things are compactly supported and they have like good causal relations between them, then more or less we can say that the statistics are independent. We can try to turn it around to extend relativistic causality through quantum informational measures to situations in which, say, the detectors are not strictly space-like separated. So there's not that strict partial order that comes from the background to the interactions. Although, as we will see in more detail later, there are good reasons to not be satisfied with this, since this type of causal factorization is indeed not sufficient, at least in higher orders in perturbation theory, if you care about that. So let's address the point one. This is some work that we did with Maria Papageorgiou and Eduardo Martín Martínez in 2023. So when the interactions are not compact, one cannot discuss relativistic causality exactly, because the detectors interact with the quantum field in the whole of space-time. So, and this may be something that comes either from effective models in which we don't have infinite resolution on the localization of the interactions, or it can be a technical reasoning because you would like to have some analytic functions that describe your interaction. And all these considerations require to consider non-compactly supported interactions. Then to discuss relativistic causality with detectors that are mostly localized around the region when it's a quantitative measure of signaling. So what we did in this work was define signaling as the ability to estimate settings through local statistics. And for that, we linked this notion of signaling with the one of quantum metrology. In particular, we estimated that in this kind of detector models, given a concrete detector model, there is good reasons to have that as an input to say that the causal relations in between this kind of inputs that, for instance, if you put something that is exponentially localized in a region, then you calculate the Fisher information in a leading order, and you see what kind of Lycon emerges depending on the parameters of the model. So what we did here, for instance, was to plot the Fisher information of a detector A with respect that is at the origin with respect to another detector B. And what we saw is that there is the Fisher information actually behaves like a Lycon in some sense. That is in this diagram, what this plot is the approach to the fuzzy localization, let's say, of a detector B that in space and time. So this is all I wanted to say with respect to this, because there are still things to be analyzed here. But I think it's more important that that we move on to something that has caused a lot of has been studied a lot in recent years. There's the so-called Sorkin's superluminal signaling or impossible measurements. So this is something that was proposed, or like a problem or an issue that was proposed by Raphael Sorkin in 1993 in the general context of quantum theory. There is that the measurement of, let's say, a global property, like whether the system is in a one-particle state of the vacuum, in a region O2, let's say, can enable the superluminal transmission of information that is contained, let's say, in a region O1 to a third region O3. So this is not about outcome correlations, because this measure was envisioned as non-selective. It is that really there is superluminal signaling in this setup. So if you want a review of how this problem came about and what solutions have been proposed, I recommend you this paper by Doreen Fraser and Maria Papageorgiou that was published in 2024. So what we did in 2021 was analyze this problem from the perspective of particle detector models. And what we so it turns out that detectors in causal contact, despite what we said that, for instance, space-like separated detectors cannot signal to each other, can display superluminal features, because causal factorization coming from the microcausality of the field is not enough. If you want also to study, to get informed about some more in-depth analysis of this, and also with a historical account of these factorizations conditions, I recommend this paper by Robin Simmons, Marius Christodoulou, and Czeslaw Bruckner that just came out a couple of days ago. So, but what we did there in 2021 was to ask, okay, consider an arrangement of two detectors, the one that is going to be used to measure and another one that does some operation, such that, and also with some information that is in space-like separation from, let's say, the part that's going to measure, and in causal contact with the party that is implementing the operation, So what happens there is that what we're asking is, can this measuring detector get access to this information enabled by the fact that there is another operation here generated by a second detector? Is there, that is, can a detector model act as a supernominal repeater? So it turns out that the matter of fact is that non-relativistic dynamics implement this type of impossible measurement supernominal signaling type problems. And the reason is, the way we encoded it, that the currents associated with the detectors are non-zero in space-like separation. So there is, these currents are not, in general, when the detector is modeled as a non-relativistic system, as the dynamics are not microcausal themselves. So we realize also that if the interaction region has no spatial extension, there is no problem with this. So this actually has to do with the spatial extension of the detector in space and time. You can think about it like this. If this was a line, there is no way that you can have an object that is space-like separated from this information and in causal contact with this other one. Second. So this led like a modest classification of causal detector models. So in order to avoid supernominal signaling, we saw that the currents associated with the detectors have to be microcausal. That is, that they have to be zero in space-like separation when the commutator there. So it could be that all interactions are defined in a coarse-grained reference frame, and small supernominal features are to be respected in the sense of effective theories. That is, if you have an atom, you would expect that, I don't know, that in some reference frame the non-relativistic approximation holds. The problem with this business of using non-relativistic detector models is that one often would like to aim to describe situations in which observers are relativistic relative to each other. There is the relative velocities between observers are relativistic. So if one really wants to describe that kind of situation, one is left with three options. One is that this current is a quantum field. The second option is to have a quantum control model in which the evolution is scalar. And the third option is, well, as I was saying, that the support of these currents is a time-like trajectory. So that's what we call the point-like models. So as we will see, there is a trade-off because each option has its pros and cons. Okay, quantum field detectors. Well, from the point of view of doing fundamental physics, makes sense to use quantum field detectors because in principle, one would think that whatever the system you're dealing with is, there is, well, in the relativistic limit, it has to be treated as a quantum field, not as a non-relativistic system, right? So there are problems with this that depend deeply on what you want the model for. For instance, free space fields are difficult. That is, fields that are defined on the whole spacetime are difficult to associate with observers because whether the field you make an approximation to give it some feature that looks like an observer, that will be some that is state dependent because if you have a relativistic theory, one could kind of like go around this thing by defining fields in boxes that move covariantly along some trajectory. And indeed, I think this is a good way to go for many applications because these boxes have many desirable properties. And there's been many works recently talking about this from Thales, Rick Perch, Jose Polo, John Malocco. I think many people are working with this. So the problem with this, there is other problem that happens even at the level of putting a field in a box, that the vacuum noise is built in the detector, and makes difficult to make claims that are often done in quantum information that involve ideal measurements. And most of all, the problem with quantum field detectors is that they are technically challenging. That is, the math is difficult, without approximations that jeopardize the locality of the claims. That is, the more local you make the claim, the more the complexity of the calculation you want to make, no matter how you want to do it. And there's also the problem that the models that rely on relativistic light matter interaction are governed by QED, which is governed by an asymptotic series at the fundamental level, and therefore, if one would like to make some sort of a non-perturbative argument, sometimes that is going to be very difficult in this context. So in the case of quantum control models, I will say here, because I know that many people use this kind of thing, that these quantum control models are causal. Perhaps you've seen some other works in which they also call quantum control things that they may have problems with the causality. What I mean here is that the currents commute in space-like separation because they commute everywhere with themselves, right? So they can be interpreted in terms of relativistic internal degrees of freedom of the field we're dealing with. So that's what makes sense then. That's the reason why it makes sense that they're causal. And they can be used to describe things like the coherence or what they're called ideal pointer variables. They're also used often in the context of quantum reference frames, but the problem with the quantum control models is that they cannot account for phenomena such as particle detection because they require particle absorption, or entanglement harvesting because these quantum control models generate channels that are entanglement breaking. And now let's go to point-like models. Well, I mean, okay, you will think, obviously, any point-like model is clearly unphysical because every realistic system is going to have some extension. However, I would say here that the goal of a detector model is to make claims about how different observers or groups of observers interact with quantum fields. So in the same way that one wants to make this type of claims for observers independent on their internal features in classical physics, like test particles, one wants to models that are insensitive as possible to peculiarities of the realistic systems that they attempt to describe. Because, for instance, on a first step, you wouldn't care how you detect a particle when you're in an accelerated motion, for instance, but you want to be able to make the prediction. And that's what makes particle detector models powerful, and that's what makes their claims general. So the danger with using point-like models is that they're ill-defined mathematically always. So distributional Hamiltonian, that is Hamiltonians that are defined as a distributions over time, are mathematically singular because the scattering operators that are associated with them are given by time order series, and you cannot time order something that is distributional because of the UV divergences that you encounter. So this is not something that is unique to quantum mechanics. Happens also when you consider Brownian motion, or even at the non-relativistic level. It happens when you consider Limblad equations, in which you consider the lamp shift of some free field, in which the environment has, let's say, not a spectral cutoff. So point-like models have to be renormalized, and it is unclear from the onset that this can be done consistently at the non-perturbative level. So I would also say here that with respect to point-like models, renormalized models represent size-insensitive situations, and their macroscopic derivation may not be the same as their bare counterparts. So if you start with a model and then you normalize it, the macroscopics of that may be very different depending on how you normalize it. Okay, so let me take the last 15 minutes to talk about a toy model that we developed with a student, Alejandro Blanco and Luis Garay from the Universidad Complutense in Madrid. Let me say first that we didn't develop, but it is more, let's say, accurate to say that we extended some models that were already in the literature to account for the kind of things that we wanted based on our previous discussion. So consider a harmonic oscillator that interacts linearly with a quantum field in this point-like manner. There is, if you forget about the left-hand side of the equalities, what we get is the harmonic oscillator in proper time, and we have the Klein-Gordon field on the other. And what we see here is that what I've introduced is a switching function that regulates where the interaction happens. And I'm also introducing an interaction that is centered always around some time-lag trajectory that is described in this model covariantly. So don't get scared if we forget about relativity and we forget about the switchings and all that stuff. This just describes a quantum harmonic oscillator that is coupled to the field amplitude at the point, and that such that the oscillator sources back to the field that fulfills a wave equation. This is what is known as quantum Brownian motion in the literature. It's not this reference here is not that we invented the thing. There are plenty of articles about it, but it's more for you to see the references therein. So what we did in this model upstairs was to generalize this kind of quantum Brownian motion story to general trajectories and to switchings and general background spacetimes. Second. So what are the techniques that one uses with this system that are different from the kind of things that we've seen so far? So the first thing is that we solve for phi and we get a particular solution that is given by the retarded solution of the Klein-Gordon equation, which we know that exists and is unique in a globally hyperbolic spacetime, plus a homogeneous solution that we realize is the free solution without the coupling. So it's basically this for linear dynamics, one can get the interaction picture exactly. And also this phi zero, this is the unique solution such that the field was free before the interaction, because one could solve this equation for many Green's functions. So when we reintroduce this form in the equations of motion, what we see is that the harmonic oscillator starts having, has a part that is independent on the field, and this is key, and is solved by the field in the interaction picture. Now, the harmonic oscillator fulfills an integral differential equation that is non-autonomous in the sense that it's not translation invariant because of the switching functions that we put, because we can have effects coming from the non-stationarity of the vacuum or the non-stationarity of the trajectories. So the problem here is that the retarded propagator cannot be evaluated along a time-like trajectory. And you can see that from the general theory on how these distributions behave and whether this can be reduced to some manifolds. There's like a analysis, that kind of analysis called microlocal analysis, and uses concepts such as wavefront sets and so on. And one can say in all generality that this distribution cannot be evaluated along trajectories without running into non-integrable singularities, at least in 3+1 dimensions. So what we do is we renormalize this distribution in a way that it's like a slight extension of a procedure that is used in more formal approaches to quantum field theory. There's called Epstein-Glasser renormalization. And we define the renormalized propagator as this object here that is the normalized retarded solution evaluated along the trajectory. So obviously the equation is not Markovian since it has a memory kernel K, which is to be expected that given that this is a non-perturbative treatment of an open system. But what is important here is that the memory kernel is independent on the initial state of the field, and that's a consequence of the so-called superposition principle, because the background is given by a linear field. So this linearity implies that under general conditions, which we can discuss, the solution for the reduced dynamics takes the form of a homogeneous solution of the integral differential equation, plus a particular solution that includes only field degrees of freedom. So, and what is important is that this propagator that generates the field amplitudes that enter in the statistics of the oscillator after the interaction becomes smooth. That is, for t greater than the support of this guy here, the switching, we get a well-defined function that mirrors the field along the trajectory. And the question now is whether that is a well-defined operator. So it turns out that the field operator, in the sense, is an operator value distribution, but and the sense in which this gives you well-defined operators depends on the representation. So what we can show is that the representations coming from Hadamard states are such that this operator value distribution can actually be made compatible with the evaluation along time-length trajectories. So, and now, because we get that this function R multiplied by chi is a smooth, compactly supported function over S, then actually what we get is that the field amplitude that we get after the interaction, that is the scatter, let's say, oscillator amplitude, is a well-defined operator. And that means that we've been able to normalize the theory at all orders. The situation can be extended to more detectors. Note that in this case, when we're considering arrangements of detectors, each detector goes around their own proper time, and what we get is a system of coupled harmonic oscillators that couple non-locally, and each of them with a distinct parameter that is given by their own proper time. In this case, the interactions between detectors do not need normalizations if the trajectories do not cross. So, and we note here from this equation, it may not look like that because it looks a little bit messy, but the interaction between the detectors is causal. That is, the only detectors influencing the dynamics of other detectors are the ones that intersect the causal path. So we have a renormalized causal model in this case. And in particular, when all the detectors are in space-like separation, what we see is that all the equations become independent. And the only way that the detectors can, let's say, get correlated through each other is if this field operator here is has in its initial state some correlations, as we will see. Second. So then the solution after all the interactions have happened in this case is given by the same kind of thing that we get for the single detector, where in this case all the phi's will be localizable in space-like separation, therefore will commute. If we recall the notion of induced observable, that is to trace the degrees of freedom of the detector to see what we're measuring, well, we get this a very simple form for product observables, that is when you get some quadratures, even non-linear things between the detectors, what you end up getting are the same type of functions that you get, that you started with some convolutions. That's a technical thing that I don't think is worth discussing now, but you get a product of observables in space-like separation. So that means that the causality here is under control at all levels. Not only that, but the non-perturbative nature of this calculation implies that the norms of the operators are under control. And if one measures, for instance, let's say, some violation of a Bell inequality in the detectors, then there are operators in the field that violate those very Bell inequalities. And so let me conclude. I'm right in time. Detector models play a more fundamental role in relativistic quantum physics because operations have to be implemented causally and locally. So if one wants causality from the onset, one has to choose between, let's say, quantum control models that implement at the level of channels pure the phasing in case you're familiar with that, it'll define interactions at the mathematical level or things that are perfectly okay as quantum fields envisioned as prose, but that they may be very challenging at the non-perturbative level. Or even at the perturbative level if one has to do a bunch of integrals in a weird spacetime, let's say. So the thing that we propose in all honesty is this kind of models that of covariant quantum perennial motion that can be shown to be renormalizable at all orders. So basically they can be used as an extension of the typical calculations that one does with point-like models that have been done since the beginning of people using these models to discuss purely non-perturbative aspects such as measurements of non-Gaussianity, Bain inequalities, or memory effects. And I think I'm gonna jump. There were some references, some names that I wanted to, some people that I wanted to mention. But with that, I think I'm gonna thank you. And if you have any questions, please feel free to ask now.
Thank you very much, Jose, for the talk. Do we have any questions already from the audience? I see we have Robert. Maybe you want to go ahead and unmute yourself.
Yes.
Hello, Robert.
Hi, Jose. Thanks for this talk. I think it was excellent and was very valuable for me. Also, the classification you did on the detectors. I just have a small question. About the model you presented, is it possible there also, so let's say you have two detectors, but you want to make detections that are not space-like separated, but time-like separated. Does that work as well with this description?
With the quantum perennial motion.
Yes.
Yeah. Perhaps it's good if I try to show the equations because I know that the way I did it was a little bit fast and it's a little bit messy. Yeah, in this equation, imagine that you have two detectors. Then you get this retarded equation, right? So the first detector, you can solve the equation, the equation till the first interaction is over. And then the first detector doesn't see the second detector. And then that second detector acts as a source of the second detector. So then in that, for things that are have like a nice causal relations, you can also use it. So I think in many situations you can use it. I mean, the main technical problem with this equation is that the integral differential equations are very difficult. So,
Okay, thanks. Yeah, that was my question really. Yeah, great. Thank you.
Yeah, I mean, just one more small comment on this. So the difficulty on these equations is in the continuous part, rather. That you really have to know how to deal with this when these integral kernels. But if you have just delays because of communication, that happens in along like geodesics, let's say, then the solution has a nice form. Just want to say that.
Okay, do we have any more questions from the audience?
Oh,
yes, Jan, please go ahead.
Hello,
Hi,
can
Jan.
you hear me?
Yeah.
Many thanks for the nice talk. It was very clear and a nice overview. I agree with Robert. So my question would be is there if you integrate or what you presented were these three classes of different ways to detect, let's say or to model the detector. And now if you say you ignore the model of the detector and want to just look at what operations or measurements you have on the QFT of interest, let's say, is there anything known, like what types of measurements or instruments you could implement using this, like your scheme, let's say, or like the singular version?
Okay. Yeah, well, first, I want to clarify that there's people like, for instance, you or Robert that have worked on trying to see how you implement operations without all this extra structure, and I want to give you credit for that. But for this talk, I was just concerned with what happens when you actually have a detector, like when you care about that. In this context, I mean, you could ask what kind of operations are implementable with this model, right? I mean, if you do a measurement in the detector after, we've not worked that out yet. I mean, it's not very difficult. It's in this sense, this is not different from the Fuster-Verge, for instance.
Yeah.
In fact, I would say that so this would be a limiting case, perhaps, in which you take a Fuster-Verge type of scheme and you focus on one mode that behaves in a certain way.
Yeah.
I would guess that that's the case, or at least it's describable or formal equivalent.
Yeah. I was thinking like maybe because you also connected, you said these are like basically Brownian motion models used in Brownian motion and so on. So maybe that one can infer like, okay, a specific type of noise depending on the setup of the model or something like that. Because on all these inductions, it's, I think, characteristic that you will add some noise to the probe measurement that's caused by the interaction. Like in your case, you have the singular interaction, so maybe there might be some differences with respect to, I don't know, the Fuster-Verge scheme or quantum controlled models.
I think the main difference with this is that you are able to go a little bit further because it's so simple.
Yeah.
I mean, because the fact that you could do the same with a Fuster-Verge kind of thing, right? You just write down the equations of motion and you do these two substitutions. The problem with that is that I'm not sure if the renormalization is going to be so easy because this depends a lot on the trajectory. And if this is difficult to solve for a single harmonic oscillator, to even be able to make some claim about the form of the solutions, I don't even want to know when you have two scalar fields. I mean, I want to make clear that for me, what this model has is that it allows you to say things a little bit further that if you have in a local way. Because I mean, if you have some kind of a scheme in which the detector is also a field, you can say a lot of things. To some extent, the same kind of things that you can say with this. But I mean, it becomes very, very, very demanding, even numerical.
Yeah,
So
totally. I totally agree. I was just okay. Thanks a lot. Yeah, I think you
thank
answered.
you for asking. Thank you for asking.
Yeah.
Can I make a question?
Go for it. Yes.
I don't know if you told this in the middle of the talk, but maybe it's just me who didn't get it. Because in the very end of your slides, you mentioned in the conclusion Bell inequalities, but most of the time I think your initial motivation was detectors that overlap, right? So how do you talk about, I mean, of course you can talk about Bell inequalities even without space-like separation, but do you say that Bell inequalities in this weaker sense without considering spatial separation, maybe just some independence, or that there is some hidden thing I didn't get do you get my question?
Yeah, I think so. Sorry for maybe the exposition wasn't clear because I wanted to split all that business about non-compact interactions very sharply from the kind of things the kind of problems that detectors have when they're not relativistic, right?
Okay.
So all that stuff about non-compact interactions is that, okay, once you have a causal model, you can ask whether quantum information of things can be defined in an effective theory in such a way that you can define causal relations that are not strict at the level of spacetime, but they're strict but they have like some kind of operational meaning. So, I mean, we didn't pursue that much in that sense, much further than what we did. But that was a perturbative calculation because in that context we showed that there is not this kind of other problems that show.
Okay, so let me see if I understood. You are trying to expand your understanding of the quantum information notions using this new description. I don't know if it's a new formalism or just a different description or a different concept, but you are trying to bring Bell inequalities in a different way of understanding that.
Sorry, I got carried on. I didn't say anything about the inequalities in the end. No, the Bell inequalities are that we're envisioning to analyze are in strict space-like separation.
Okay. You're not considering the overlapping only with detectors and Bell inequalities. You're not doing that.
I mean, it is a very fair question because, but I think that the problem is, as far as I understand it, that problem is already in non-relativistic physics, right? Because if you allow for a little bit of signaling, it's not clear what to say over like whether you have a local realist model that implements that or not. This would be a nice setup if that problem was already solved in the non-relativistic case.
Okay.
But I think doing that with this model would be overkill without having solved first the conceptual problem at the non-relativistic level.
Okay, thanks a lot.
Thank you for asking.
I think we lost Catherine. So there's someone else who would like to make any question. So I will take the chance to ask a curiosity of mine. So I'm aware that in general there is no experiments for detectors yet, right? But or am I wrong?
I could talk for hours about that, but
okay. No, I mean, my question to you is that if you can like somehow, if your results they are something on the some foundational thing for understanding the foundations of the theory, or could you prove some of your results on some experiment, even though challenging? Could you propose some experiments to check something, check your result?
Well, I mean, this was more about model building because it's based on at this point long tradition of using these models to discuss things that are theoretical physics in the deep level, like what happens with black holes when you have relativistic accelerations and so on, right? But the way I envisioned this was always more like, okay, you use it to improve on that kind of analysis to describe, say, new phenomena that are non-perturbative, or like to discuss things that have to do with measurement theory, with quantum information, how to tie the two things, right? At the experimental level, there are many challenges, I would say. The first one to say that this thing is pointless.
Okay.
So how the effective field theories, let's say, interplay in curved spacetimes and what kind of experiments you would try to do there. Can you get away with this if you don't have a black hole next to a particle accelerator or something like that? This I don't know. I mean, I don't think there's much experimental prospect for the kind of phenomena I'm particularly interested in, but I mean, there's also a lot of talk that one can do, even at the level of saying whether this switching function that I'm writing down there makes sense.
Okay.
Because you're switching an interaction from the vacuum, for instance, which is something that only makes sense in a coarse-grained sense, and it's not very clear that it's local and all that stuff. There's like much to say about whether.
The general question I have: how do you control the switching function for choosing something first of all in the beginning of all, right? So it's something that is indeed challenging.
It is, yeah, and overall it is a problem, but the more of a problem is that if you don't have this kind of objects, you cannot even discuss causality in a meaningful way. So yeah, I think there's much to be thought about in the years to come about how these things come about. But thank you for the question. It's very pertinent.
Thank you very much. It was much clearer now.
Okay, do we have any more questions? It seems today we're sticking perfectly to the scheduled time, both of the talk and the Q&A session. Okay, if there's nothing else, then yeah, let's thank maybe digitally José again for this talk.
Let me thank you for the invitation.
Very welcome, yes. All right, then I think we wrap it up and we thank you again and look forward to the next seminar.